The origins of the V-2 rocket lie in the interwar period, when advances in rocketry began attracting the attention of both scientists and military planners. Germany, constrained by the Treaty of Versailles in developing long-range artillery, turned instead to rocketry as a potential way to bypass restrictions on conventional weapons. By the early 1930s, a small group of engineers and enthusiasts at the Verein für Raumschifffahrt, VFR, the German Society for Space Travel, experimented with liquid-fueled rockets. Among them was Werner von Braun, a young engineer whose work would become central to the development of the world's first operational ballistic missile. Von Braun's early experiments, conducted under the auspices of the German Army Ordnance Department from 1932 onward, laid the foundation for the V-2. The military's interest was straightforward: a weapon capable of striking enemy cities from hundreds of kilometers away, bypassing defensive lines entirely. Such a system would not be limited by terrain, weather, or traditional artillery ranges. The Heeresversuchsanstalt Peenemünde, Army Research Center Peenemünde, was established in 1937 on the Baltic coast as the main facility for large-scale rocket development, providing the space, technical infrastructure, and secrecy needed for the ambitious project. The V-2, formerly designated Vergeltungswaffe 2, Vengeance Weapon 2, was envisioned as both a technological breakthrough and a strategic weapon of retaliation designed to strike Allied cities in response to bombing campaigns against Germany. Its design combined cutting-edge propulsion, guidance, and materials technology. The rocket would stand 14 meters tall, weigh approximately 12.5 metric tons at launch, and be powered by a liquid-fueled engine burning a mixture of ethanol and liquid oxygen. It was intended to reach speeds of up to 5,000 miles at 160 km/h, altitudes of around 90 kilometers, and deliver a 1,000-kilogram warhead over a range of approximately 320 kilometers. One of the major challenges was the guidance system. Engineers developed a gyroscopic autopilot to maintain the rocket's course, and a pair of aerodynamic fins and graphite vanes within the exhaust stream for control during powered flight. This technology was unprecedented for the time and required extensive testing and refinement. The rocket's structural materials also posed difficulties. The high stresses of acceleration, combined with the extreme temperatures of combustion, demanded new alloys and manufacturing techniques. The program's technical ambition was matched by its scale. Peenemünde expanded into a massive complex employing thousands of engineers, technicians, and laborers. The German military allocated substantial resources despite competing wartime demands, driven by the belief that the V-2 could become a decisive strategic weapon. However, the program was also shaped by internal political pressures, with the SS increasingly involved in its management and production. By the outbreak of World War II, the basic design principles of the V-2 were in place, but the leap from concept to operational weapon remained formidable. Early test flights would expose the difficulties of scaling up from experimental models to a reliable, combat-ready missile. Yet the strategic vision, an unstoppable weapon that could strike at the heart of enemy cities without warning, remained the guiding objective, ensuring continued investment in what would become one of the most significant technological developments of the war. The prototype and testing phase of the V-2 program began in earnest in 1942, following years of incremental progress with smaller test vehicles such as the A3 and A4 models. The A4 designation was the technical name for what would later be known as the V-2, representing the first fully realized version of the long-range ballistic missile concept. Peenemunde's facilities allowed engineers to construct large-scale prototypes, integrate propulsion and guidance systems, and conduct live firings along the Baltic coast where extensive instrumentation tracked each flight. Initial launches revealed a host of technical problems. Early prototypes suffered from structural failures during ascent, instability in flight, and premature engine shutdowns. The liquid-fueled engine, producing roughly 25 metric tons of thrust, required precise control of fuel flow and combustion chamber temperatures, both of which proved challenging. Engineers had to address combustion instability, which could cause catastrophic explosions on the launch pad or in mid-flight. The guidance system, using gyroscopes linked to servo mechanisms controlling aerodynamic fins and exhaust vanes, also required extensive calibration to prevent the rocket from veering off course. Breakthroughs came through a methodical program of testing and redesign. Stronger airframes using improved steel alloys reduced structural failures, while refinements in the fuel pump and combustion chamber design improved engine reliability. Graphite vanes placed directly in the exhaust stream provided more responsive control during the boost phase, and adjustments to the gyroscopic autopilot increased accuracy within the limits of the technology. Each successful launch brought the missile closer to meeting operational specifications, though accuracy remained relatively poor by modern standards. Impact points could deviate by several kilometers from the intended target. On October 3, 1942, the program achieved a critical milestone when a prototype V-2 was launched from Peenemünde and reached an altitude of 84.5 kilometers, traveling 192 kilometers downrange and impacting the designated target area. This flight marked the first human-made object to reach the edge of space in a ballistic trajectory, validating the fundamental design. German military observers recognized its potential as both a psychological and physical weapon, capable of delivering a large warhead faster than any existing defense system could intercept. Following this success, the transition toward operational production began, but testing continued to refine performance and reliability. The Peenemünde test program launched dozens of V-2s, each yielding data on flight dynamics, fuel efficiency, guidance precision, and warhead detonation reliability. These tests also highlighted the logistical and operational challenges of deploying such a weapon. Launch sites would require mobile platforms, fuel storage and handling for cryogenic liquid oxygen, and a large trained crew for each missile. By 1943, as the Luftwaffe's dominance waned and Allied bombing intensified, the German leadership pushed for accelerated V-2 deployment. This urgency coincided with Allied awareness of the program, leading to targeted air raids on Peenemünde in August 1943. While the raids damaged facilities and delayed production, they did not halt the program. Development and testing were partially dispersed to alternative sites, and preparations for large-scale manufacturing at underground facilities began. The prototype phase had proven the V-2's feasibility, but operational readiness still required solving issues of mass production, field deployment, and crew training. The groundwork was laid for its transition from an experimental rocket to the first combat-ready ballistic missile in history, ready to be used in a strategic campaign against Allied cities. The V-2 entered operational service in September 1944, with its first combat launch targeting Paris and later London. Deployment was managed by specially formed units under the German Army, with the Waffen-SS also heavily involved in operations. These units were equipped with mobile launchers, fuel trucks, and support vehicles capable of setting up and firing a missile within hours, then relocating before Allied aircraft could respond. This mobility made the V-2 fundamentally different from traditional artillery, as its launches could be conducted from forests, fields, and concealed rural locations far from established bases. Early operational use was concentrated on London and Antwerp, chosen for their strategic and psychological value. London represented both a political and symbolic target, while Antwerp's port facilities were critical to Allied logistics after the liberation of Belgium. The missile's supersonic speed, nearly 5,760 km/h, meant it struck without warning. There was no practical defense once launched, as radar could detect it only seconds before impact. This made it a profoundly unsettling weapon for civilian populations, adding a new dimension to strategic bombing. However, the transition from testing to real-world deployment exposed limitations. Accuracy remained poor, with many missiles missing their intended targets by several kilometers. This meant the V-2 was most effective against large urban areas but largely unsuitable for precision strikes against military installations. Reliability was also variable. While some missiles performed flawlessly, others suffered engine failures, mid-flight disintegration, or guidance malfunctions. Despite these issues, German command valued the V-2 as both a retaliatory measure against Allied bombing and a means of demonstrating technological prowess. Operational logistics were complex. Each missile required careful fueling with liquid oxygen and ethanol, processes that had to be completed shortly before launch to prevent fuel evaporation or freezing. The fueling operations themselves were dangerous, as any mishandling could result in catastrophic explosions. Transporting the rockets to launch sites demanded specialized trailers and cranes, and crews required extensive training to handle the mechanical, electrical, and fueling systems under field conditions. In combat trials during late 1944, the V-2 units refined their launch procedures to maximize survivability and effectiveness. Mobile launches from wooded areas in the Netherlands and northern Germany allowed crews to strike Allied targets with minimal warning and then quickly move to a new location. Allied intelligence struggled to pinpoint these sites in time to prevent launches, though aerial reconnaissance and resistance reports occasionally led to successful airstrikes on support convoys or storage depots. Reactions from the German military leadership were mixed. While the weapon fulfilled its role as a terror and propaganda tool, it failed to deliver the decisive strategic effect that some had envisioned. It could not halt the Allied advance or significantly disrupt industrial output, and its high production cost consumed resources that might have been allocated to other weapon systems. Nevertheless, as 1944 turned to 1945, the V-2 campaign intensified, with hundreds of missiles launched in a final attempt to slow Allied progress and inflict maximum damage before Germany's defeat. By the end of its first months in service, the V-2 had proven itself as a groundbreaking weapon, fast, unstoppable once in flight, and capable of causing significant destruction in urban centers. Yet its operational role was constrained by the realities of wartime logistics, limited accuracy, and the inability to produce it in number sufficient to alter the strategic balance. The next phase of its history would see the V-2 used in a sustained combat campaign, testing its tactical value and exposing its true impact on the war's final stages. The sustained combat use of the V-2 began in earnest during the winter of 1944-1945, as German launch units increased the frequency of attacks on Allied-held cities. London and Antwerp remained the primary targets, with The Hague in the occupied Netherlands serving as one of the main launch hubs. The choice of Antwerp reflected its strategic significance as the principal supply port for Allied forces advancing into Germany. By disrupting port operations and damaging surrounding infrastructure, German planners hoped to delay the Allied offensive and buy time for defensive preparations on the Western Front. Operational patterns developed quickly. V-2 launch crews operated in small mobile teams capable of setting up a missile, fueling it, and firing within 2 to 3 hours. After launch, they would dismantle the site and relocate to avoid detection. These shoot-and-scoot tactics exploited the missile's mobility and the Allies' inability to intercept it in flight. The supersonic descent of the V-2 meant there was no audible warning before impact, unlike earlier V-1 flying bombs, which could be heard approaching, giving civilians no time to take cover. In London, impacts caused widespread destruction and civilian casualties, with some strikes killing dozens in a single explosion. Antwerp suffered particularly heavy bombardment, with missiles targeting dock facilities, warehouses, and nearby residential districts. Despite these attacks, the V-2 campaign failed to achieve the intended crippling effect on Allied logistics. Damage to the port was repaired quickly, and shipping operations continued at high tempo. The weapon's limitations in accuracy and payload became increasingly apparent. While the 1-ton warhead was lethal against soft targets and unfortified structures, it lacked the destructive capacity to neutralize hardened military installations. The missile's circular error probable, often several kilometers, meant that even when aimed at specific strategic sites, many warheads detonated in open areas or less significant locations. The psychological effect, however, was considerable. The inability to intercept the V-2 before impact contributed to a pervasive sense of vulnerability among civilians in targeted cities. Tactically, the Germans attempted to adjust the missile's employment by varying launch sites, timing, and trajectory parameters to complicate Allied countermeasures. Allied intelligence worked to identify and disrupt the V-2's supply chain, targeting fuel depots, transport routes, and production facilities. Resistance groups in occupied Europe provided valuable intelligence on launch preparations, occasionally enabling airstrikes on launch convoys before they could fire. However, the dispersed and mobile nature of the V-2 units made total suppression impossible. By early 1945, as Germany's military situation deteriorated, the V-2 campaign reached its peak intensity, but also entered its final phase. Hundreds of missiles were fired in the war's closing months, yet their impact on the overall strategic situation was minimal. The cost in resources and labor was immense, especially given the growing shortages of fuel, skilled personnel, and manufacturing capacity. In the end, the V-2's combat use revealed it to be a weapon of significant technical achievement, but limited practical effect in altering the war's outcome. It inflicted casualties, damaged infrastructure, and demonstrated a capability no other nation possessed at the time, but it could not change the course of the conflict. The lessons of its deployment, both in its successes and shortcomings, would strongly influence post-war missile development and strategic doctrine. Variants and technological evolution of the V-2 rocket developed both during and after its operational service, as German engineers sought to improve its range, accuracy, and efficiency. While the original A4 configuration served as the standard combat model, experimental modifications and derivative designs were pursued at Peenemünde and other research facilities in an attempt to address its known shortcomings and to explore potential new applications. One area of immediate focus was improving guidance accuracy. The wartime V-2 relied on a relatively simple gyroscopic autopilot system, which could keep the missile on a stable trajectory but was prone to cumulative drift over the course of its powered flight. German engineers tested more advanced guidance techniques, including radio command updates and more sensitive gyroscopes, but wartime conditions and production pressures prevented widespread adoption of these refinements. Efforts were also made to experiment with different trajectory profiles to improve impact precision and reduce fuel consumption, but these adjustments had limited success within the constraints of the existing design. Range and performance enhancements were another area of development. Proposals for the A4B variant incorporated aerodynamic wings to extend the missile's range by enabling a partial glide phase after rocket burnout. Test flights in late 1944 showed mixed results. While the concept demonstrated potential for greater reach, stability issues and structural stresses at high speed limited its immediate practicality. Another ambitious project, the A9-A10 combination, was conceived as a multi-stage rocket capable of striking targets on the U.S. East Coast from Europe. The A10 would serve as a massive booster stage, propelling the A9 into a long-range trajectory. This concept was never completed, but laid theoretical groundwork for later intercontinental ballistic missile designs. Alternative payload configurations were also explored. While the operational V-2 carried a high explosive warhead, discussions were held about fitting the rocket with unconventional payloads, including chemical weapons, though these were never implemented. There were also proposals to adapt the V-2 for reconnaissance by replacing the warhead with a camera package and parachute recovery system, allowing for photographic intelligence from inaccessible or heavily defended areas. These concepts remained experimental and were never operationalized during the war. Post-war, the technological evolution of the V-2 accelerated as captured rockets, components, and technical documentation were studied extensively by the Allied powers. The United States, through Operation Paperclip, brought key engineers, including Wernher von Braun, to work on American missile and space programs. In the Soviet Union, reverse-engineered V-2s, designated R-1, served as the starting point for a series of increasingly capable ballistic missiles. The British also conducted test firings using captured V-2s to gain experience with large liquid-fueled rockets. These post-war adaptations often included upgraded materials, refined propulsion systems, and improved guidance technology. The legacy of the V-2's design was thus embedded in the earliest generations of both military ballistic missiles and space launch vehicles. While the original wartime variants saw only limited technical evolution due to the pressures of production and combat deployment, the underlying engineering principles of the V-2 became the foundation for decades of missile and space exploration technology worldwide. The global impact and legacy of the V-2 rocket extend far beyond its wartime use, shaping both the trajectory of modern warfare and the dawn of the space age. As the first long-range guided ballistic missile ever deployed, the V-2 demonstrated that a weapon could be launched from one country, travel through the edge of space, and strike another nation without interception. This capability fundamentally altered strategic thinking, introducing the concept of rapid, transnational strike potential that would later underpin the doctrine of intercontinental ballistic missiles, ICBMs. In the immediate post-war years, the V-2's influence was felt most strongly in the United States and the Soviet Union, the two emerging superpowers who quickly recognized the strategic implications of such technology. Operation Paperclip in the U.S. brought over 100 German engineers and scientists, including Wernher von Braun, to work on American missile and space projects. They contributed directly to the development of the Redstone missile and ultimately the Saturn V rocket that carried astronauts to the moon. In the Soviet Union, captured V-2 components and documents were reverse-engineered to create the R-1, which evolved into increasingly advanced missile designs under the leadership of Sergei Korolev. This parallel technological inheritance from the V-2 played a central role in the Cold War arms race. The United Kingdom also benefited from post-war access to V-2 technology, conducting its own series of test launches, while France, through cooperation with former German scientists, later developed early rocketry programs influenced by V-2 principles. In this way, the missile's design legacy spread across multiple national programs, often serving as the technological template for early liquid-fueled rockets. The V-2's engineering breakthroughs were equally significant for civilian space exploration. Its successful use of a large liquid-fueled engine, stabilized guidance systems, and aerodynamic controls provided the basic architecture for future space launch vehicles. Early atmospheric and space science experiments in the United States used captured V-2s to study the upper atmosphere, cosmic rays, and microgravity effects, marking some of the first scientific missions to the edge of space. These experiments bridged the gap between wartime missile research and peacetime space science. Culturally, the V-2 left a complex and controversial legacy. On one hand, it represented a leap forward in human technological capability, showcasing engineering achievements that were decades ahead of their time. On the other, its wartime use as a weapon of terror against civilian populations and the exploitation of forced labor in its production at the Mittelwerk facility tied its legacy to human suffering and war crimes. This duality, technological brilliance built upon moral atrocity, remains a defining aspect of its historical narrative. In museums and memorials today, the V-2 is often presented in both contexts, as the forerunner of modern spaceflight and as a symbol of the militarization of advanced science. Its place in history is secure, not only as a weapon that influenced the outcome and tactics of the Second World War, but also as the technological seed from which much of the 20th century's missile and space technology grew. The V-2's legacy is thus both a warning and an inspiration, proof of what human ingenuity can achieve, and a reminder of the consequences when such ingenuity is applied to destruction rather than exploration. Beyond its well-known operational history and post-war technological influence, the V-2 rocket story includes lesser-known chapters that reveal additional dimensions of its development, use, and legacy. Some of these involve experimental applications and secret projects pursued during the final years of the war, while others concern the ways in which the missile was adapted for research purposes in the years immediately following 1945. During the war, German engineers explored several ambitious variations of the V-2 concept that never reached operational deployment. One such project was the A-4B, a winged version of the V-2 intended to extend its range by adding aerodynamic lift during the ballistic descent phase. This design was tested in late 1944 and early 1945, with at least one partial success before the war ended. There were also advanced concepts such as the A-9A-10 Amerika Rakete, a two-stage intercontinental missile theoretically capable of striking the eastern United States from Europe. Although work on these projects remained largely on the drawing board, they demonstrated that German rocketry research had already moved beyond regional targets to intercontinental ambitions. Another little-known wartime adaptation was the proposal to launch V-2 rockets from submerged platforms at sea. This concept, intended to circumvent Allied bombing of land-based launch sites, envisioned modified U-boats carrying and erecting rockets for surprise attacks on coastal cities. While technically possible, the system never progressed beyond the planning stage due to resource constraints and the deteriorating German war situation. In the immediate post-war period, both Allied and Soviet forces used captured V-2s for scientific purposes. In the United States, these rockets became test vehicles for upper atmosphere research. Experiments conducted from the White Sands Proving Ground between 1946 and 1952 gathered valuable data on temperature, pressure, cosmic radiation, and solar ultraviolet light in the upper atmosphere. Cameras mounted on these flights produced some of the earliest photographs of Earth from near space altitudes, marking an important step towards space-based observation. In the Soviet Union, beyond the reverse engineering of the missile for military use, engineers also used the platform to test guidance methods and stage separation techniques that would later appear in space launch vehicles. These experiments indirectly contributed to the launch of Sputnik in 1957 and the subsequent era of space exploration. Another overlooked aspect is the role of V-2 testing in the development of rocket recovery systems. Several post-war experiments replaced the warhead with scientific instruments, and equipped the nose section with parachutes, allowing for recovery and reuse of data packages. This concept anticipated later practices in space research, where safe recovery of experimental payloads is essential. The V-2 program also left an enduring mark on the organization of large-scale technical projects. The logistical demands of building, transporting, fueling, and launching such complex systems under wartime conditions provided a template for managing future missile and space programs. The need to integrate engineering, manufacturing, logistics, and operations into a coherent whole foreshadowed the project management structures of the Cold War's missile race and space programs. These lesser-known elements of the V-2's history underscore its role as far more than a single wartime weapon. It was a technological testbed, a foundation for later aerospace research, and a platform for ambitious, if unrealized, concepts that anticipated many of the advances in rocketry that would define the mid-20th century. In both its operational and experimental forms, the V-2 demonstrated the dual-use nature of advanced technology, with applications ranging from strategic bombardment to scientific exploration. The final phase of the V-2 rocket's history unfolded in the closing months of the Second World War, when the weapon's operational use continued even as Germany faced inevitable defeat. By early 1945, the Allies were advancing on all fronts, and the strategic value of the V-2 was increasingly questionable. Despite this, production and launches persisted, both to maintain pressure on Allied cities and to serve as a demonstration of technological capability. Antwerp, London, and Liège remained frequent targets, with launches conducted from increasingly improvised sites as fixed facilities were overrun or destroyed. Logistical constraints became severe. Fuel shortages, disruption of transportation networks, and the loss of trained personnel reduced the number of rockets that could be launched. Manufacturing, already heavily reliant on forced labor at the underground Mittelwerk facility, was strained by Allied bombing raids on component suppliers. The quality of late-war V-2s varied, with some missiles suffering from defects due to rushed assembly and inadequate testing. Reliability, which had been a persistent issue even at the program's peak, declined further under these conditions. Operational units adapted to the worsening situation by making launches from smaller, more dispersed sites, and by reducing preparation times. However, as Allied forces advanced into the Netherlands and Western Germany, the territory available for launch operations shrank rapidly. By March 1945, the number of operational firings had dropped significantly, and several launch units were either destroyed in combat or forced to surrender. Even in its last weeks, the V-2 campaign inflicted casualties and damage, but its strategic impact was negligible. The weapon had failed to alter the course of the war, serving primarily as a psychological weapon rather than a decisive military tool. For the German leadership, however, continued use of the V-2 had propaganda value, demonstrating that Germany could still strike at distant targets despite the collapse of its front lines. As the Allies captured Peenemünde, Mittelwerk, and other key facilities in April and May 1945, they seized rockets, components, and technical documents in large quantities. Competing efforts by the United States, the Soviet Union, and the United Kingdom aimed to secure as much of the V-2's technological and human resources as possible. Engineers and scientists were interrogated, recruited, or in some cases detained for extended periods. This scramble for German rocket expertise marked the beginning of the post-war missile and space programs in both East and West. The end of the war did not mark the end of the V-2's influence. Captured examples were quickly shipped abroad for testing and reverse engineering, forming the basis for the first generation of Cold War ballistic missiles. In this way, the final operational months of the V-2 were less an ending than a transition, shifting the rocket from its role as a wartime weapon to that of a foundational technology in the emerging era of global missile development and space exploration. The operational record of the V-2 rocket, measured in numbers and outcomes, reveals both the scale of its deployment and the limits of its effectiveness. Between September 1944 and March 1945, approximately 3,200 V-2s were launched in combat, with the majority targeting London, Antwerp, Liège, and other Allied-held urban centers. London alone endured over 1,350 impacts, while Antwerp suffered more than 600 strikes, making it the single most heavily targeted location. Casualty figures vary, but in London, the V-2 campaign killed an estimated 2,700 civilians and injured around 6,500 more, while in Antwerp the toll reached into the thousands. From a purely technical standpoint, the V-2 achieved what no previous weapon had, striking a target hundreds of kilometers away with a supersonic, high-altitude ballistic missile. It was immune to interception by contemporary air defenses, rendering traditional anti-aircraft systems ineffective. This invulnerability in flight set it apart from the earlier V-1 flying bomb, which could be intercepted by fighters or flak. Yet, despite these advantages, the V-2's military effectiveness was undermined by its limited accuracy, high cost, and the enormous logistical effort required for each launch. The missile's circular error probable, measured in kilometers, meant it was best suited for large-area bombardment rather than precision strikes. Against sprawling urban targets, it caused destruction and casualties but could not consistently hit specific infrastructure such as docks, factories, or military headquarters. This limitation significantly reduced its ability to inflict lasting damage on Allied logistics or command structures. In Antwerp, for example, port operations continued despite heavy bombardment, with damaged facilities repaired quickly and shipping schedules maintained. In economic terms, the V-2 program was costly. Each missile required advanced materials, specialized components, and large quantities of ethanol and liquid oxygen, all of which were scarce in wartime Germany. The use of forced labor at the Mittelwerk facility reduced monetary costs, but introduced inefficiencies, quality issues, and moral atrocities that remain an inseparable part of the V-2's legacy. From a strategic resource allocation perspective, many historians argue that the vast resources consumed by the program could have been directed toward weapons with greater battlefield utility. Despite these shortcomings, the V-2's psychological impact was disproportionate to its material effect. Its silent, high-speed approach left no opportunity for warning or defense, creating an atmosphere of fear in targeted cities. Civilian morale was tested, though the overall will to resist among the Allied populations remained intact. For German propaganda, the weapon served as a symbol of technological prowess and resilience, even as military defeat became inevitable. The statistical record thus paints a clear picture. The V-2 was a remarkable engineering achievement that proved the feasibility of long-range guided missiles. But as a wartime weapon, it was more significant for its symbolic and psychological dimensions than for its tangible military results. In this respect, it was a weapon that foreshadowed future strategic missile systems more than it shaped the tactical reality of the Second World War. The long-term influence of the V-2 rocket lies in its role as the technological bridge between wartime weaponry and the Cold War's strategic missile and space programs. While its operational contribution to Germany's war effort was limited, the principles it proved, liquid-fueled propulsion, guided ballistic trajectories, and high-altitude flight, became the foundation for the next generation of rocket development worldwide. In many respects, the V-2 was less important for what it achieved in 1944-1945 than for what it enabled in the decades that followed. In the United States, captured V-2s and the expertise of German engineers accelerated ballistic missile research by years. Programs such as the Redstone and Jupiter missiles drew directly from V-2 engineering, while NASA's early launch vehicles retained clear design lineage. In the Soviet Union, the reverse-engineered R-1 and its successors established the technical base for the world's first intercontinental ballistic missiles and the launch of Sputnik in 1957. Both superpowers applied lessons from the V-2 to navigation systems, fuel management, staging concepts, and thermal protection, all critical for both weapons and space exploration. Doctrinally, the V-2 reshaped thinking about strategic warfare. It demonstrated that a missile could bypass conventional defenses entirely, striking deep into enemy territory without the need for aircraft or the risk of interception. This realization influenced the development of deterrent strategies in the nuclear age, where the capacity to deliver a warhead over great distance with little warning became a cornerstone of military planning. The concept of mutually assured destruction, which dominated Cold War policy, had its technological roots in the capabilities first demonstrated by the V-2. Its legacy, however, is inseparable from the moral and humanitarian dimensions of its creation and use. The V-2 program relied on forced labor under brutal conditions at Mittelwerk, where tens of thousands of prisoners from concentration camps were exploited, with many dying from overwork, starvation, and mistreatment. These human costs cast a shadow over its technical achievements, ensuring that its history is remembered not only as a milestone in engineering, but also as a cautionary tale of scientific progress in service of destructive ends. Today, surviving V-2 rockets are displayed in museums in Europe, the United States, and Russia, often accompanied by detailed accounts of both their technological significance and the human suffering linked to their production. They stand as artifacts marking the beginning of the missile age, connecting the final years of the Second World War with the opening chapters of the space race. In the broader arc of history, the V-2's most enduring impact lies in proving what was possible, ushering in an era in which humanity could reach beyond the atmosphere, for both war and exploration. It remains a symbol of the dual-edged nature of technological advancement, capable of redefining human horizons while carrying profound ethical consequences that continue to resonate in debates about the role of science in conflict.